What you are looking at here is an emission line spectrum for atomic hydrogen. What we've got set up here is over here on the left is a tube that's full of hydrogen gas. And it's being zapped electrically here. So the gas is good and hot. The photo, though, is being taken through a diffraction grating. So you have between this light source here and the camera is a diffraction grating. And so what you're seeing off to the side are a few specific colors of light. It turns out that these exact colors of light that make up the overall hue that you see here are unique to hydrogen. And in fact, using more sensitive equipment, you could even tell whether you're looking at the isotope of hydrogen that's just one proton, or whether it's a proton and a neutron, by the wavelengths of the light being very slightly different. So we'll go ahead and use this as our entry point for a quasi-historical treatment of the development of the theory of the hydrogen atom and more broadly quantum mechanics and atomic physics. And so we'll start this by an observation made by Kirchhoff. Yeah, the same one who had the rules about electric circuits. The guy kind of got around. So these are known as Kirchhoff's rules of spectroscopy. And what Kirchhoff noticed was that there were three different kinds of spectra that you could have. And he was sort of thinking of this more in like context of looking at distant stars or something like that. But let's say we have some hot black body radiator, a star, whatever. Anything that's emitting light just because it's hot. If we have an unobstructed view through our diffraction grating, so this is an eyeball here looking at our through our diffraction grating, what you'll end up seeing here is a continuous spectrum. And I'm just going to indicate that by showing that you are getting all the colors of the rainbow. Now, as we've seen earlier, some colors will be brighter than others, and the brightest wavelength will be given by Wien's displacement law. He then said, well, what if we had some cloud of cooler gas over here? It turns out that depending on which angle we're taking looking through the light, looking at the light, if we look right through the gas over to the star, what you wind up seeing here is a continuous spectrum with some specific colors missing. This is what's known as an absorption line spectrum. And if you go and look at the gas at any other angle through our diffraction grating, what you end up seeing is the emission line spectrum that I was showing you earlier. Now, these don't have to be exact negatives of each other, and we'll get into why that is later. But there will be there will be corresponding lines. It turns out that what's going on here is, and we'll develop the theory of this as we go on, light coming in here, if it happens to be the exact right wavelength, will cause transitions in the electron energy levels of the atoms or molecules. And then those will radiate back down. And when they do, they'll emit the light in every direction. Now, the black body radiation light is so much stronger, and only a little bit of whatever's being emitted here goes this way. We end up getting dark bands here. But if I look over here, that's all you can see is what got emitted from the atoms and molecules de-exciting. It'll turn out that with our absorption line spectrum, most of the time when we work out energy levels, we'll be only looking at transitions that involve the n equals 1 energy level, whereas the emission line spectrum can see all sorts of different energy level pairs. But it turns out, so the picture I showed you there would look different if it were a different molecule. We'll get into that eventually. But it turns out that for hydrogen specifically, an astronomer by the name of Jakob Balmer, just playing with numbers, was able to make an empirical fit for all of the wavelengths of the light that you could see from a emission spectrum of atomic hydrogen. So Balmer's empirical formula, which we will eventually derive, says that the wavelength of the emitted light works out to be 91.18 nanometers divided by 1 over m squared minus 1 over n squared, where n and m are both integers, and n has to be greater than m, which makes sense because we want this to be a positive number. So we need n to be bigger, so this is smaller than that, so that the difference is positive. We've since generalized this a little bit, and it's often now written this way, where 1 over lambda is equal to a number called the Rydberg constant times 1 over m squared minus 1 over n squared, where this Rydberg constant is equal to 1.097 times 10 to the 7 inverse meters. Either one will give you the right answer, and will give you all of the wavelengths of light that you can that we've ever detected from hydrogen. But what's more of interest here is with a fit like this, where it's playing with, where it neatly gets organized using these integers here. While it's not a guarantee, theoreticians look at phenomenological fits like this, and their alarm bells start to go off, because this suggests that there's some sort of underlying structure to the atom that drives this. So we'll hold that thought for a moment, and then we'll jump over from Switzerland, where this was being developed, over to Australia. And this is an experiment due to Ernest Rutherford. Although the really fun parts of it were due to Geiger, as in Geiger counter, and an American graduate student by the name of Marsden. Anyway, what Rutherford did was he took a very thin layer of gold foil and he launched alpha particles at them. An alpha particle is a helium nucleus. So to read all this apparatus of numbers here, He, that is the symbol for helium. 2 is the atomic number, means the second position in the periodic table. 4 is the mass number, meaning it has 4 nucleons. So since the atomic number is the number of protons, this means that there are 2 protons and 4 protons plus neutrons, which means 2 protons and 2 neutrons. It's also doubly ionized. So we're just looking at the nucleus. Anyway, these alpha particles I can't even draw them to scale compared to the gold foil. If I were to try to draw it to scale compared to the gold foil, I wouldn't even be able to draw a pixel. So anyway, he would fire these alpha particles at the gold foil, and what pretty much what everyone expected was that there were you'd see slight deflections of the beam sometimes as the alpha particle got close to a gold atom. Now, the big surprise, though, was, and this is due to the diligence of the graduate student Marsden. The way they detected these things was they had screens that had a phosphorescent material on them. So whenever an alpha particle hit it, the screen would light up. They would sit there and watch them for a certain amount of time and count how many landed on the screen, move the screen, and keep it up. One of the issues that people were worried about was that there could be some level of background radiation that had to be corrected for. And it's also actually a real problem that if you stare in the darkness for long enough, sometimes you think you see flashes of light. So as a check, Marsden decided to stick some of the detectors on the same side of the foil as the alpha particle. And much to everybody's surprise, occasionally this would light up. And they realized it wasn't because their eyes were playing tricks on them. It wasn't because of background radiation. It was because occasionally the alpha particle was yoinking back like that, which was a real surprise. So this phenomenon here is known as backscattering. And where Rutherford gets the credit, because Geiger and Marsden were the ones who were doing the bulk of the lab work, the reason Rutherford gets so much of the credit was he was able to interpret what was going on, and he made a fairly radical suggestion for how the structure of the atom had to be. Up until this point, the electron had already been discovered, but the proton and neutron hadn't yet. And so at this point, the best model of the atom that people were working with was one due to J.J. Thomson, known as the plum pudding model. And this refers to a certain kind of British treat that gets served at Christmas, where you take leftover rendered fats and you make sort of a pudding out of it, or sort of like a some sort of a starchy cakey kind of thing, I think, and you stick plums into it to make it taste better. And anyway, Thomson's proposal was that you had basically positively charged goo in which you stuck the negatively charged electrons in. So you can think of it as like taking some jello or something like that. Imagine the jello was the positively charged bit, and then push some raisins into the jello or something, saying that that was the negatively charged bit. Those are the negatively charged bits, and that was the best model the people had at the time. There were very good reasons for them not to think that the nucleus had to be ridiculously small. But Rutherford's experiment showed that that was how it had to be. When Rutherford did a careful analysis of this, he hypothesized that about the only way you could explain the extreme backscattering that he was seeing was if the structure of the atom had, say, had electrons orbiting the positively charged nucleus. So this would be our gold atom. I'm not about to draw the requisite number of electrons for a gold atom, but the idea would be our alpha particle would fly in, and what Rutherford observed is that occasionally it must fly close enough. It flies into the electron orbits, gets close enough to get repelled by the nucleus. Most of the time, say if you had something more glancing, you'd be doing something like this, or up here you'd be basically undeflected because you'd be seeing the positive and negative charges mostly canceling out. But very occasionally, if the alpha particle was more or less lined up with the nucleus, you would get this backscattering event. Now, this is another one of those issues where I can't possibly draw this to scale. This nucleus has to be about 100,000 times smaller than the electron orbits. Which is what leads me to my favorite fact about, amazing fact about nature for me, which is that basically everything you see around you is pretty much completely empty space. If the diameter is 100,000 times smaller, that means the volume is going to be 1 with about 15 zeros times smaller than any of the electron structure. And the electron, for all we know, could be a point particle, but in any event, it's very small indeed. So pretty much everything you see around you is almost completely empty space. So it was a pretty wild idea to bring this up, and it was only because Marsden had detected this backscattering. Now, Rutherford made the most minimal incremental change that he possibly could to the idea of the atom, and he just riffed off of the idea of planets orbiting the sun. So this is why it gets known as the planetary model of the atom, replacing gravity with the electric force. However, a quick bit of computation shows that there's a problem with the planetary model. The problem is this. Say here's my positively charged nucleus. I've got an electron orbiting around like so. The issue here is that as the electron changes direction, this it means the electron is accelerating, and this is actually going to cause the production of an electromagnetic wave. The fancy name for this kind of electromagnetic wave is Bremsstrahlungen. That's the singular, Bremsstrahlung, and the en makes it the plural. It comes from German, and it means braking radiation. Just like if you hit the brakes on your car, it accelerates, right? It accelerates negatively, but it accelerates. And so it's the same kind of idea here. Change the speed or change the direction of motion of a charged particle, it will emit an electromagnetic wave. And the energy to do that has to come from somewhere. And where that somewhere is the kinetic energy of our electron. So here's the problem. Let's try that again. So here's the problem, is that if you calculate this up, very quickly our electron should crash into the nucleus. Classically. Now, this, of course, can't be the case because we're still here and we're made of atoms. So, obviously, everyone knew that this couldn't be the case, but try as you might with doing classical calculations, you couldn't get around this. All right, so entering the stage now will be the Danish physicist Niels Bohr. And the key thing here with Bohr's model is this is an ad hoc explanation. In other words, it's constructed to give the right answers. But there's no real theoretical justification to it. I'll say yet. So basically, Bohr's going to put out there, and he's going to say, in order for us to see what we're seeing, that we're seeing the discrete spectrum, for instance, because one of the issues here is as our electron goes into a death spiral, this ought to be a continuous spectrum, which we don't see. And so in order to get a discrete spectrum, and in order for the atoms to still be here, he purports he puts together an ad hoc explanation that goes like this. The key points of this are that the electrons go in circular orbits. He eventually modifies that thought just a bit, but this is his first pass at it. Due to the electric force. So just like Rutherford said, it works just like a planet orbiting the sun, but we replace the electric gravity with the electric force. Now, what about the issue that you're supposed to have Bremsstrahlung? Well, he says that certain stable orbits don't brem. And by the way, this is actually really sloppy physics slang because English-speaking physicists find saying Bremsstrahlung and to be a mouthful. We will often, especially when it's being used as a verb, we'll just say brem and call it a day. He then says, okay, and our radiation, so when we do see light, it's emitted by an orbital jump. And he even has to go so far as to say that the frequency of this radiation being emitted is independent of the orbital frequency. If you remember when we talked about electromagnetic waves earlier, this is kind of counterintuitive here because what we're saying is you take a pile of charge and you shake it up and down. That's how you make an electromagnetic wave. And the frequency of the wave is the frequency at which you shake the charges up and down. So you would think that would be the orbital frequency, right? I've got my positively charged nucleus here. I got my electron here. This is specifically the hydrogen atom that Bohr is worried about at the moment. So he's saying, we're always going at some tangential velocity like that. Electricity's providing, the electric force is providing the centripetal force, and we're going around some radius r, whatever. And you think about it, if I'm looking from over here, I'll be seeing the charge go up, down, up, down, up, down, up, down, relative to this direction here with the orbital frequency. But the problem is, you calculate the orbital frequency, it has pretty much nothing to do with the emission of any of the light that we see. So Bohr says, hey, no problem, that is apparently not how it works. That's mighty convenient. And also, he's going to need to require that angular momentum. Angular momentum is quantized. Now, this is an ad hoc explanation, but even so, it works far better than it has any legitimate right to. But at the end of the day, remember what Bohr is saying is these are the things that just in order to see, in order to match the Balmer's fit, in order to be able to see discrete emission spectra, in order to actually still have atoms around, these are the key points that an atom has to obey. And we have to figure out what's going on that under the hood that makes that happen. So let's go ahead and play with this a bit and see what we can recover from this. So his radiation condition. That's saying the energy of an emitted photon will be equal to the initial energy level of one stable orbit, of the higher stable orbit, minus where you ended up. And the angular momentum quantization condition says that L is equal to n h bar, where n is a integer, and h bar is now I'll say this is kind of by definition is Planck's constant over 2 pi. This is sort of fading out in the physics literature, but there are still a handful of variables where you'll see physicists putting a bar through the variable like this. And what this is just a shorthand for divide by 2 pi. So if you hear me say h bar, that just means Planck's constant divided by 2 pi. Occasionally people will take a wavelength and divide it by 2 pi. You do that, you would write lambda bar sometimes. It's starting to fade out just because it's so much easier to typeset this fractions now than it used to be. But h bar is probably going to be with us for the foreseeable future just because of how much it's used. All right, so with that, let's go and take a look at our electron that is orbiting our proton. Let's see what we can figure out about that. So that is our orbital radius. We are orbiting due to the electric force, and there is our tangential velocity like that. So if we remember back, for a point charge, the potential energy due from a pair of point charges would be K times this charge times that charge. Well, one is a plus E, the other is a minus E, so that'll be minus KE squared over R. So that's the potential energy of the electron-proton pair. Let's see if we can figure out the kinetic energy. So for the kinetic energy, the way we can start with that is to identify that the electric force is our centripetal force. So our any centripetal force has to be equal to mv squared over r, and our centripetal force here is going to be equal to k q1 q2 over r squared. Well, our q1 and our q2 are both e's, and we're working in magnitude, so we don't sweat the minus sign. So ke squared over r squared. Okay, so we can cancel that, and then what we can do is we can go ahead and times this by 1/2, so I get kinetic energy, as long as I divide by 2 there. So I end up getting that the kinetic energy is equal to plus ke squared over 2r. So that means that the total mechanical energy, which is going to be the kinetic plus the potential, that's going to be equal to plus ke squared over 2r plus a negative ke squared, just plain over r. So this winds up being minus ke squared over 2r, because I multiply top and bottom here by 2. So that's the total mechanical energy, which turns out to be 1/2 of the potential energy. This actually turns out to be an application of a broader idea known as the virial theorem. So it turns out that this sort of thing pops up a lot in orbital mechanics. All right, so that's what we've got so far. Now, for our stable orbits are going to be the ones that satisfy this quantization condition right here. So let's go and look at that. So starting from the angular momentum quantization condition, that has to be equal to nh bar, we remember that the angular momentum for a point particle is always equal to mvr. Okay, I can rearrange this and get that v is going to be nh bar over mr. And again, if I want to have a 1/2 mr, so this would mean if I squared this, that v squared would be all this stuff squared, n squared h bar squared over mr squared. Okay. So to get my kinetic energy, remember the kinetic energy is 1/2 mv squared. So, sorry, m squared there. So if this is v squared, I multiply this by m, I'll lose 1 power there, and divide by 2. N squared h bar squared over 2mr squared. Okay. Now this is a mouthful here. So what we usually do is we break out this bit of it right here, and this turns out to be a I'm sorry, I'm not quite there yet, my bad. So anyway, I've got my kinetic energy, and it has to be equal to my the other expression I had for my kinetic energy, which we found was KE, which was capital K, KE squared over 2R. Okay. Now, if I rearrange this, I will get that that my radius of my orbit will be equal to n squared times, this gets either written as a naught or a sub b, where this a sub b is equal to h bar squared over m k e squared. This is known as the Bohr radius. Yeah, I can spell Bohr radius. And this number turns out to be 0.0529 nanometers. So we can put an n subscript on this and say that the radius of our nth allowed orbit is that. Okay. If I substitute that back in into my energy equation, so I'll just say we're just substituting it and I'll skip the algebra. We will get that the energy of my allowed stable orbits will be equal to k minus k e to the 4 over 2 n squared h bar squared. The only thing that really matters here is the n, and usually people just pre-compute all the rest of it and say minus 13.60 eV over n squared. And this matches up beautifully. If we use this, we can go ahead and recover using the radiation condition for the photon. We can recover the Balmer formula, and in fact we can look at all of the different energy levels, all of the different series. So what we end up having is here's our ground state at n equals 1. This is minus 13.6 eV. Then n equals 2 will be that much, minus 13.6 eV over 2 squared. Then this would be minus 13.6 eV over 3 squared for n equals 3. And then while we're at it here, we can talk about 4 and 5. And it turns out that, for instance, all the transitions that you can see in the visible, these all turn out to be transitions down to n equals 2. This is what's known as the Balmer series. And so this will be transitions from n to 2. It turns out to be another series in the ultraviolet, which is every possible transition down to n equals 1. I should say visible and a little bit outside. This is the Lyman series. These are all transitions down to 1, and this is in the UV. All the remaining ones are transitions down to the are in the infrared. So for instance here, let me bring that in like that. Transitions down to n equals 3, for instance. That's the Paschen series. That's in the infrared. Transitions down to n equals 4 are the bracket series. Then transitions down to n equals 5 are the Funt series. And I mean, this goes all the way up to infinity. I'm just running out of room to draw this. And so these are all in the infrared and longer. So this works. And in fact, you can also make it work for other single electron systems. For instance, if you strip one electron off of helium, you get a similar thing, except you have to track the atomic number around because the charge of the nucleus changed. Or doubly ionized lithium, or whatever. As long as you strip all but one of the electrons off, at least until you get to really high atomic numbers, this actually works really well. Now, Bohr doesn't suggest how any of that is coming about, and that will be the subject of the next video. So catch you over there.